All right, let's talk about constants next, because we'll work with constant numbers quite a bit. So integer constants, floating point, character, and string. So constants are literals. In our Hello World program, we saw a string of constant characters, right? HELLO, WRLD. So constants are numbers or identifiers whose value does not change while the program is executing. So we'll see how to create a constant identifier. Right? Variables can change their value anytime, but constants can never change their values. The value of a constant is always known at compile time, and they may be of any of the basic data types that we've already seen. Integer constants, floating points, so character constants, string literals, they can be short. Any of those types. So an integer literal, it can be of base 10 decimal, octal, or hexadecimal constant. But we have to say what base we're working in. When we work in decimal by default, but if we want to specify the base or the radix, we use 0 small case x or 0 capital X for a hexadecimal number. We use 0 in front of a number for octal, and we don't precede a decimal number with anything. So by default, we work in decimal or base 10. Remember that the octal integers consist of a set of digits 0 through 7, but we want to write octal literals in C, 0, 1, 2. So this preceding 0 here says that this constant is an octal constant. Here the number 0, well 0 is 0 in octal, it's 0 in hex, it's 0 in decimal. And that's how we'd write 0 in octal if we wanted to. Here, 1, 2, 3, 4, in order to specify that this is an octal or base 8 number, we precede it with a 0. There's examples of hexadecimal integers. Remember, they contain the digits 0 through 9 and then A through F. That's base 16. Right, so we have 16 different digits. We can use the X can be upper or lower case. So we want to specify then here that we have a hexadecimal value of FEE. We precede it with a 0x, and see the F can be capital, it can be small. We've got E and E both in small case. You can mix the cases, it doesn't matter. Here, hexadecimal value of 1, 2. So it's a constant literal value, 0x. Notice all of these are preceded with 0x. So here's how we do 0 in base 16, hexadecimal. Or you can use the capital X to indicate hexadecimal as well with a 0xA4. Finally then, as I said, we use base 10 by default. So decimal integers contain the set of digits 0 through 9. So if you were to write 0 or the number 12 or the number 931, right, these are base 10. They're not preceded with a 0 or a 0x. By default, the data type of an integer literal, so these were literals, literal constants, is int. So the data type is int. Right? Not short, not long, not char, but int. Right? So if you were to go ahead then and write 1234 or 1234, the compiler assumes the data type is int. This becomes more important later when we're trying to assign like types and we have warnings enabled to let us know when we're not doing that. Right? We want to keep in mind data types at all times to make sure that we're not trying to assign a type that's too big to a type that's too small. Now, if you want to go ahead and specify that the number should be unsigned, right? Because remember, int is signed by default. If you want it to be unsigned, you can use a capital U or a small u as a suffix. So we add suffixes to the number. We use capital L or small l for long. Here's some examples. If you want to take the 1234, the 1234, and specify that this was an unsigned number and not just an int, so now it's an unsigned int. The U here, or the U here says this is an unsigned int data type. If you want to force this to be a long data type, we put an L after the number. If you want it to be unsigned long, you can use any one of these four, UL, U capital L, any of these combinations for unsigned long. Like I said, you don't have to memorize this right now. What's really important to remember right now is the data type is int. later, if you're working with some unsigned and signs and longs and you get warnings, you're going to have to cast these or use these suffixes to make them a particular type. We'll see that later and go through it again. Floating point literals. The data type then is a double, the default data type. Right? So if you were to type 0.02, the data type of this is a double. All of these are base 10 numbers. Right? We tend to write base 10 for floating point. We don't write hexadecimal floating point or octal floating point. We work in base 10. So minus 1.23, the data type is a double. If we were to then write something like this, 789.456, this plus operator then stands for addition. And we were going to add 0.36 to that number. This is going to form a constant literal value, right? This value does not change. You can add the suffix f to a number to make it floating point. So uppercase f, lowercase f. So if you don't want it to be a double, we add the f afterwards then to each one of these. And once again, I went to the end. I didn't want to go to the end and go back up to our constants. So let's go back to, all right, slide 47. Actually then, right here, this isn't very clear. The slide should be improved. Okay, I just added a tab character here. If we were trying to add two numbers together, they would be a constant. Let's make it clear that we can precede these with a plus or a minus sign as well. By default, if we don't put a plus sign in front of a number, we assume it's positive. Here is an example where we're saying this is positive 0.36. Normally, we're not going to type this because it'll be positive without the plus sign. All right, so back on slide 47, you have to be careful with this mouse button. We have the suffix f here for floating point. So these numbers are all the same as here. We've just added the suffix f to make the data type floating point instead of double. Like I said, we'll see later. We don't want to assign floats to doubles, doubles to floats. That will become important. So for right now, just know that you can do this. We'll come back later, and chances are you'll have to look this up again to see how to do this when we use it later. We can also write floating point numbers in exponential form. But we can use the smaller the lowercase e to write exponential form. So if we wanted to say 0.5 times 10 squared, we'd say 0.5e2. When there is no plus sign here, we assume that this exponent is 2. Exponent means you're going to take the number to the left and multiply it by 10 raised to the power to the right of the e. So 14e minus 1 is the same as 14 times 10 to the minus 1. 1.2e to the plus 3, so you can add a plus if you want to indicate the sign, is the same as 1.2 times 10 cubed. Sometimes exponentials are an easier way to write numbers. Okay, finally, character constants. A character constant then is surrounded by single quotes. So if we want to assign the value of the letter A to something, we put a character constant inside single quotes. If we want to assign a pound sign. So these are all going to be keys you find on your keyboard. And if we're working with character types, it will be important to assign character constants. Remember, everything's in single quotes. This is a character 1. This is a character uppercase Z. Later, when we learn about printf, we're going to learn about some escape sequences. And if we want to assign the value of an escape sequence to something, well, an escape sequence has a backslash followed by a letter. This is actually that new line character we saw in Hello World. This then causes a carriage return in a line feed. Basically, it moves the cursor on output down to the start of the next line. we'll see that the escape sequence \t stands for tab. That will tab the cursor over on output. \b is actually a backspace character. And \r just brings the cursor back to the start of a new line. Because we'll see these examples when we start working more with printf. Characters are then stored using the machine's character set. CodeBlocks is using an ASCII character set, and we'll use an ASCII character set this semester. If you're using Xcode, Xcode is using Unicode. If you're using Microsoft Visual Studio, they're also using a Unicode version. Okay, string constant. Oh, a character constant is a single character. Sorry, that mouse wheel got me again. All right, so a string constant is surrounded by double quotes. So you can have a single character in there, but the double quotes means to treat this as a string. A string, we will learn later, is a special data type. It's an array of characters. So an A in double quotes is not the same as an A in single quotes. And we've seen hello world before. Here's the string of characters. So each one of these is an individual character. We call it a string because they're inside double quotes. So if we wanted to write the string literal hello, or the string literal character for character 1, 2, 3, ABC, we would write it like that. All right, we'll come back and talk about strings later and see how to use string constants. Right, now, if you want to declare an identifier name, a constant. Right, a variable is something whose value can change. We want to create a constant. The value of the constant will not change. So we're going to use the keyword const, and we're going to add that to the start of our variable declaration. Here's an example. Then const int is a data type, integer, max. So our variable name is max. When we declare it, we immediately have to assign a value to it. Right? Well, we go ahead and say max will be assigned the value of 10. And anywhere we use max in our code, it will have the value of 10. Here, if we want to make a constant value for pi, we can give it a data type of double. The keyword const says we cannot change what's stored in here. So we originally initialized this with this value. When we use pi later, we cannot change its value. And right here, const data type is char, variable name is key. We're going to store the letter B in this. So anywhere we use key, it'll be the same as using the character B. All right, so const keyword specifies that the value of these identifier, these variable names, cannot change. We also have another way of creating const values that are just a little bit different than this const. Another preprocessor directive. Right. So the preprocessor directive, remember a preprocessor directive, a compiler directive is what this is, always starts with a pound sign. Now the word define. So we've seen pound include for header files. Well, pound define will use it to declare constant values as well. So we can place a pound define anywhere in a program. Typically we place them at the top of our program. So here's some examples. And instead of using const and data types, if I say pound define max and give it the value of 10, remember by default, this literal 10 is an integer data type. Anywhere in code that we use max, the compiler will substitute the value of 10. When you then use these preprocessor directives, these are also called macros as well. We do not use the assignment operator, and we do not end them with a semicolon. But we want to create pi, pound define pi, and then here's how we give pi a constant value. Pound define key, and it's a character constant, so it's still surrounded with single quotes to indicate that is a character. Right. So similar to this, use the same names. Didn't use the keyword const, did not use the assignment operator, and they don't end with a semicolon when we have the preprocessor directive. The difference between the two is when we create these with the keyword const, memory is actually allocated. Special memory is allocated for this, where these variables are stored. Right? Anywhere we use these values, this is the value that's associated with it. When we use a macro to do it or a preprocessor directive #define, the compiler simply substitutes these values anywhere where these letters, these identifier names are used. By convention, we usually name const values in all uppercase so that when you look at a program and see something in all uppercase, you assume that that's been a preprocessor directive or a constant. All right. Now, we also need, then this slide is telling you that you can't have any blank spaces between the # and the define, so no blank spaces. But you have to have a blank space between the word define and what you're going to name the macro. And then you also have to have a blank space after the name. At least one, you can have multiple ones. Right? This is not a C statement. It doesn't end with a semicolon. And we don't use the assignment operator with it. Right. Now, why do we use constants? All right. So in this example, I'm going to assume that we've written a program for a grocery store. And we've created two macros here, preprocessor directives. One's called sugar cost per pound. One's called flour cost per pound. Notice these are good identifier names. If they're used in code, it's a lot easier to understand that we're talking about the cost per pound of sugar than if we just use 99 everywhere. Right? The same way flour cost per pound. Let's assume then we've written code and we've used this wording sugar cost per pound everywhere. Well, if we want to change the value of the cost of the sugar, all we need to do is change the value here and then recompile the program, and it will resubstitute all the new values, as opposed to if we had just hard-coded in 99 into our program. Suppose our program was 1,000 lines long and we had to search, and everywhere we searched and found a 99, we needed to change the value. Well, we have two values that are 99. One's for sugar, one's for flour. We're only changing the price of sugar. But if we're not careful in our code and we just use find and replace to change all the 99s, we'd also change the cost of flour. So we use these constants because they're easier to read in our code so that we know exactly what we're talking about in our code. And then it's a simple change. If we need to change this value, we change it at one place in the code, recompile it, and the compiler resubstitutes in that value, that new value everywhere. So the constant method is easier to maintain and it's less error prone. So we will make good use of constants this semester. All right, finally, let's talk now about ASCII. ASCII is how characters are represented in memory. All right, so if you're writing a character, if you're typing on the keyboard and you type the letter A, how is that stored in our program's memory? How is that represented? We have to have some way to map an A to binary values, because remember, everything on our digital computers is stored in memory as binary digits, bits. Bits are binary digits. So we want to map that. The one encoding method is called ASCII. It's a single byte character code, so single byte meaning 8 bits. It was originally based on the English alphabet, and it encodes 128 specified characters into 7-bit binary integers. So they only use 7 bits, right? They left the 8th bit, which later was used to expand ASCII to extend it. But originally then ASCII, that first 128 values of ASCII, those 7 bits then, can represent the numbers 0 through 9, the letters A through Z, small and uppercase, blank spaces, and several control codes. So we'll take a look at the ASCII table in just a second. ASCII is not used as much anymore, right? It was based on the English alphabet originally. English is not the only language in this world. Now, Unicode is a scheme that the computing industry came up for. It's a standard then for encoding. And basically, Unicode wraps in ASCII for the first 128 values, but now we can represent text expressed in most of the world's writing and language systems. So Unicode is more commonly used because computers are worldwide and there are multiple languages. All right. ASCII stands for American Standard Code for Information Exchange. Right. The tables, then we're going to see the ASCII table that's divided into these different control characters, printable characters, and extended character set, right? It was originally designed to help us print things out. back in the 60s, people didn't have these, well, there weren't personal computers. A lot of times they didn't have monitors. They typed things in on punch cards and they got information printed out on paper. But we needed to know then how to control the printer as well. And that's where these control characters come from. Right, so here's an ASCII table. And here are the 128 encoding values. The ASCII table will give you what a decimal value is, what a hex value is, and what an octal value is. It doesn't give us the binary, right? But we are going to look at the character value. So null, and we'll talk about the null terminator later, is actually stored in memory as the binary version of 0. So here's our decimal numbers going from 0 down to 31, 32 to 63, 64 to 95, 96 up to 127. Right. So this first part we said were printer control characters. So start of heading, start of text, this was to help us print things out on forms to move paper through a printer. These codes were actually sent then at times. Well, at times they were sent to the printer. If we needed a backspace, if we needed a horizontal tab, if we needed to move up a line, we need to vertically tab. So all of these characters were used to control a printer. We don't really use them anymore. We can sometimes use them in your terminal and your console to move things up and down. Like I said, for the most part, these are no longer used. Right. What we'll be concerned with, starting here with a decimal value of 32, is the space character. So when you're typing on the keyboard, when you're running your code, you're often going to be typing on the keyboard to enter information into a program. It's going to have to map those keys. But same way, when you want to print out that information to the console screen, it's going to map those keys. And it has to know how to store things in memory. So when you hit your space bar, well, your space bar is stored as the binary equivalent of the decimal 32. The asterisk is stored as the binary equivalent of 33. Right. Here are the digits 0 through 9. So the character 0 is represented by an integer decimal value of 48. The character 1 is represented by an integer decimal value of 49, which of course, remember, these are converted into binary. Right, so we have punctuation, there's your colon, semicolon, less than sign, equal sign. So everything on your keyboard, your computer keyboard, is represented here. We have the uppercase characters, the lowercase characters as well. Beyond ASCII then, originally, that some people extended the character sets. Now, they're not, the extension is not standard from compiler to compiler, IDE to IDE. So you don't always get the same character set. But if we were to work with code blocks, and actually then we'll do some assignments later where we work with these extended character sets to see what they print out, but they're not commonly used as much. But because we only used 7 bits originally, we had that 8th bit, they could extend it and make use of that 8th bit for the numbers 128 through 255. Now, the thing to remember about an ASCII character is it's 8 bits. 8 bits, it takes up 1 byte of memory. So you should remember in this course always that there's 8 bits per byte. Just a reminder then, each binary value between 0 and 127 are unique, and the numbers 0 to 127 only require 7 bits. So when we looked at that table, we saw that we started with a decimal 0 and ended with a 127. That's why they use the 7-bit representation. So here's your 7 bits for binary version of 0. Here's your 7 bits, all ones, 7 ones, for a binary representation of the decimal 127. All right, let's look at the alphabetic characters. The uppercase A is a hexadecimal 41. The lowercase a is a hexadecimal 61. So here's our, sorry, let me fix this. I have these reversed. All right, sorry about the error in there. We have the small case a is a hex 61. So small case a, hex 61, uppercase a, hex 41. notice that they only differ in 1-bit position. This was done on purpose because bit operations are faster than other operations. We'll see later when we learn bit operations how convenient it is to toggle a bit to go between one and the other, to convert uppercase to lowercase and vice versa. And you'll see that with the entire alphabet. There's an uppercase B, which is a hex 4-2. There's a lowercase b, which is a hex 6-2. And then here are the numeric digits, 0 through 9. So these are character values. Here's the character 0. We have to remember that the character 0 is represented in memory by the hexadecimal 30, or the decimal 48. So here are the binary representations then of the character 0, the character 1, the character 2. Right? And we'll work with this as we go on, these ASCII representations. So we want to remember that ASCII encodes the numbers. Its data type is char. Again, a reminder that the char data type uses 8 bits, and that unless we have the word signed in front of it, we don't know whether or not a char is signed or unsigned, but we have to dig into the system library. It's implementation dependent, so that's something we'll learn to check later. Right, so for right now, if you want to know something signed or unsigned in terms of a char, put that keyword in front of it. Now, assigning char values. Let's go ahead and declare a variable that's named myChar. It's of data type char. So here's the data type right here. And I did it again. I shouldn't touch the scroll wheel on my mouse. All right, here's our data type char. Let me annotate this. Here's our data type char. Here's our variable name myChar. We can use different assignments to store the same information. They're all going to produce the same result. But here's our variable name myChar. If we want to assign the character A to it, let me get my mouse cursor back here. All right, if we want to assign the character A to the variable myChar, we use the character constant, which is in single quotes. We could also assign the value of 65 because the ASCII table says the decimal value of 65 is a representation of A. We could also assign the hexadecimal value of 41 because the hexadecimal representation of A is 41. And finally, the octal representation of A is 101. So assigning 101 to myChar has the same effect. These all produce the same results. We've stored the same binary number, and myChar basically is storing the mapping of the character A. All right, let's look at some example programs.